Everybody. Hope you're doing great. Here we are coming at you, lesson 3-5. Maybe you're watching this because in class today it was a little confusing. This is a lot like domain and range, folks. It's a little bit abstract. It's a little bit weird. Unfortunately, it's going to be with us forever, okay? Because we are going to deal with these things we call transformations with all of our different functions. So our linear functions that we're working on now, we're going to see it again for our quadratic and our exponential functions. All right, well, what is a transformation? A transformation, guys, is just a movement of one graph to another place on a coordinate plane, right? So we have here a movement of a graph. Beautiful. We have different types of transformations, right? And bam, here they are. So we have translations. These are up, down, left, right moves. Okay, so we can move it up, down, left, or right, just depending upon what it looks like. Dilations, these are the goofy ones. These are vertical or horizontal stretches or compressions. This is also vertical or horizontal. No, I already said that. Stretches or compression. Good to go. Stretch or compression of a graph. It can be vertical or horizontal, right? Meaning it can get steeper or it can get less steep, okay? They will be very confusing, again, until we do about 342 of them. Then on the 343rd one, they'll get better. Reflection, that's where we're just flipping or moving a line, right? And we're flipping it over another line. Typically, it's over an axis. Sometimes, very rarely, will it be over an actual line, like, hey, the line y equals x, or something like that, okay? All right, so here we go, 3-5. Carry on with the fun. Let's take a look at it. Yep, make all that go away. There we go. Okay, probably don't need to be zoomed in as much. Okay, so we're going to start off basic with our up-down moves. Okay, so up and down moves. Again, these are your cheat sheets. Our up and down moves, guys, are controlled by a number at the end of a function. Okay? So here is my blue line. This is, remember we had parent functions a while back, right? If we have a number and we put it on the end and it's bigger than 0, right? Like +2, +4, +8, that will move it up, right? So this is an up move. The opposite happens. So this graph over here, right? If we have a negative number, right? So if we see something like -4, -2, -12, that is a down move, right? And it will go down or up by whatever that number is, okay? So again, if we add a number to the end of a function, right, whatever that number is, positive, it goes up that many units. Negative, it will go down that many units. Beautiful. So let's take a look at how this works. All right, folks, here we go. So here's my parent function, right? This is my parent function for all things linear. F of x equals x. Sometimes you will hear us say, hey, y equals x. Remember, synonyms, it means the same thing. So how is this graph related to this graph? Well, it's the same thing. It's just, right, in this case, they say, hey, g of x is x plus 8. So they both have an x. Good. What does this plus 8 do? We just talked about it a second ago. This is a number bigger than 0, so it will move up by this many units. So this graph will, I would just say, move up, and we just say 8 units. Okay? That is how it relates to our parent function. And here's the deal, guys. If you're not sure, graph it on Desmos and see what happens, okay? So if we were to graph these on Desmos, my parent function is just y equals x, guys. That literally just looks like this line right here. Goes right through the origin. It's just that diagonal line. If we were to look at this one here, I'll graph it in red. This is going to be x plus 8, right? So think about it. Where's the y-intercept? It's at 8, right? So it's going to be all the way up here at 8. It still has the same slope, just x, right? It's going to look just like that. So all that's really been done is it's moved up 8 units, okay? So there we go. If this was like x minus 8, it would do the opposite, guys. It's going to go down 8 units. Okay. Maybe we're thinking this isn't so bad. Things are going well. Okay. We also have left and right moves. Unfortunately, left and right moves are counterintuitive to what our brains think. Just like we saw +8, we went up. We saw -8, we go down. Okay, here it's going to be backwards, okay? So we will move to the right if we see subtracting a number. We will move left, right, if we see adding a number, okay? Let's see how this works. All right, wait a second. We didn't even get to see any of these. Well, that was just ridiculous. Okay, trust me, they're there, folks. Do you want me to give you a couple examples of them? Too bad. I'm kidding. We can do a couple. I'll make one up for you. Okay, so let's say we have our function, f of x equals x. Great. And they said, hey, tell me about this one. And it says x minus 4, right? How are those related? You've got to be careful with where parentheses are with all this stuff, folks. Because here's the deal. If we put it on a graph, we might be tempted to say, oh yeah, that went down 4 units. Because it kind of looks like that. But unfortunately, parentheses are kind of a big deal, right? When our parentheses are saying, hey, we want you to take x and subtract 4, it's kind of different than if we just had an x value minus 4. I know it doesn't sound like a lot, but it will make a difference, right? So this is really a right 4 unit one. If we saw the opposite of this, guys, if we saw f of x equals, and then in parentheses, x plus 4, right? Again, our brains are trained to think, oh yeah, plus 4, going to go to the right 4. Minus 4, going left 4. It's not the way this works. If we see this, again, it's got to be in parentheses. I want to be clear on this. This is a left move, right? This is left 4 units. This one up here, right 4 units. Okay? All about where we see parentheses. And it's gonna keep going with that trend here in just a second as we enter in more confusion, right? And I'm gonna flip over a slide here just real quick. We're gonna come back to that one. Here we go. So when we multiply a number now, right? So once again, f of x equals x is our parent function. If we were to multiply that x value by a number, any constant, 5, -5, 2, 1/2, 2/3, okay? We get a compression or we get a stretch, right? So a compression or a stretch. Two of these are very similar. They kind of mean the same thing. Again, it depends on, do I see parentheses or do I not see parentheses, okay? We really don't have a good place to add it in here, so we're going to add it in. We're going to add it over here, guys, okay? So I want you to write down vertical stretch, okay, slash horizontal compression. These look like and have the same effect on a graph, okay? These basically, guys, make it steeper. So we would have our normal, I'll put it in green. Here's our normal y equals f of x function. If we're going to use this terminology, which means the same thing, our line, guys, no, I don't want to be green. Our line is going to get steeper. Okay? But depending upon which phrase we use is what we would see. Okay? So if we see something that looks like this, f of x equals 5x. Okay? If we see this, f of x equals, and then in parentheses, 5x. Okay? This is my dead giveaway for which one of these I'm going to use, right? If we have parentheses around, right, our x, our input, then we're going to use this horizontal compression, right? Other way, if we have, hey, we're just multiplying this input by 5. Again, I know they look a lot alike. I know they sound a lot alike. If we see this, this is a vertical stretch, okay? All right, so there's 1/2 of this. Awesome. Okay, here comes our other ones, right? Because, not all of our numbers, guys, are going to be bigger than 0, right? So this is for any number that is, bigger than 1, okay? Maybe we should put that on here. So this is greater than 1, okay? What happens if you are less than 1? We use the opposite terminology. So instead of being, and you can say these backwards. You can say vertically stretched. You can say stretched vertically. I don't really care, okay? So we could say the opposite of being vertically stretched is being horizontally stretched, okay? The opposite of being horizontally compressed, right, is to be vertically compressed. Okay, vertically compressed. Again, if we go back to my graph, these ones aren't going to have the same slope as this one. They're going to be flatter. They're going to be shallower, right? They're going to look something like that. Okay? What do these look like when we talk about our functions, right? So if we're horizontally stretched, I should have wrote these over there. This is the one that's going to be in parentheses. So maybe this is like 2/3 x. Okay? If we're compressed vertically, we don't have the parentheses. Maybe we just look like this. 2/3 x. Okay? This could be the most useful tool for you figuring this out. So make sure you write this down. Pause the video if you need to. I'll get out of the way. Here it is. This will help you, right, when we go to describe the transformations that's happening to this. Okay? All right. So now we can answer this question up here. I'm going to keep all this here. So now we can describe this dilation. And this really should say f of x. They goofed up and put g of x. It should be f of x equals, and then in parentheses, 14x. Okay? Well, guys, 14x, again, a vertical stretch, a horizontal compression have the same effect when we look at a graph. For now, when we get into our exponentials and our quadratics, this will make more sense. But for now, we want to try to get the terminology right. We would say, hey, this is a horizontal compression, right? And then we like to add whatever number it is. So, guys, we would say this is a horizontal compression by a factor of 14, right? Again, I got 14 just because that's the number they're multiplying it by. That's how much steeper this is becoming, right? This is 14 times steeper than just our parent function, f of x equals x. Okay, fun times. You guys are good here? Of course you are. Right? That was some of my best artwork right there. All right. Okay, then we get stuff like this. Again, this should say f of x. Darn you, typos. F of x equals, here, I'm just going to write it down here so I can write it bigger. We got a negative. I have a 0.7x in parentheses. Okay, there are two things that I need to do to describe this, okay? The first thing, right, I will describe, guys, is this right here, right? What do my parentheses do? Okay, well, this is a stretch. Whoa, is it vertically? No, almost wrote the wrong word. Horizontally. So this is a horizontal stretch, or you can say stretch horizontally. And then we would just like to put in that number, right? By 7/10, 0.7. Now, we haven't seen this one yet, right? Apparently, my slides are out of order. The second thing I need to describe is this dude right here. What does that negative sign do? Well, the negative sign one, sometimes we don't think about it because we're thinking, oh, it's just negative, right? It's just going to stretch it or compress it by that number. It's just a negative number. But no, guys, this actually flips my graph over, right? So this will be a flip over, in this case, the x-axis, okay? Great. Guys ready to keep going? Oh, hold on. Hold on. My phone's ringing. I got to pause this somehow. Yes. Okay, we're back. I figured out how to pause the video, make it all come back. Okay, we're all good. So guys, we didn't see it. I don't even know if our notes talked about it. How did we know this was? Because, we could reflect over or flip, same thing. We could flip over the x-axis or we could flip over the y-axis. It all depends on where we see this negative sign, okay? If our negative sign is right here just the way it was, we flip over the x-axis. Let's just say we had this, f of x equals, and then it was negative 0.7x. This is the other one. So this will flip it not over the x-axis, but now over the y-axis, okay? Didn't have that one. Probably want to write that one down just in case we see it. I think we will. Okay. Onward we go. Okay, so a couple things to do here, folks. All right, so again, how does it relate to our parent function? So we have f of x equals negative 3x plus 2. All right, I have 3 moves that I have to describe here, okay? Here's one of them, here's another one, here's another one, okay? So I need to describe what the negative is doing, I need to describe what that 3 is doing, and then I need to describe what the 2 is doing, okay? It doesn't matter what order that you say these in. So let's just start with the negative. So the first move, right? The negative will do what? It will reflect it or flip it over the x-axis. That's right. So this is a reflection over the x. Okay? Move number 2, the 3, right? Think about what does the 3 do? It's not in parentheses. It's outside the parentheses. This is a stretch vertically, right, by a factor of 3. My last move is this plus 2. Again, inside parentheses. Okay, so this is a left or right move. Left or right move. Any guesses out there? Well, we think plus 2. We think, oh yeah, that's positive 2. It's got to go right 2. It's not, right? It's kind of counterintuitive. This really will go left 2 units. Okay? So if you know how to graph, so why do we do this, guys? If you know how to graph this function right here, f of x equals x, which of course we all do, right? This is our super, most basic function ever. All you have to do are 3 things, and then you will have my new function. You reflect it over the x-axis. You stretch it vertically by a factor of 3. That means all of those outputs get bigger by a factor of 3. And then you move it left 2 units. You do those 1, 2, 3 things, and now you have our new graph. I know, some of you are saying, well, why don't we just use Desmos for crying out loud? Desmos is the best at everything. And I would agree. Here's this one that we needed. Okay. Yes. All right, so here's what it looks like. So they said, hey, f of x equals this. G of x equals this. There you go. This is a reflection across the y-axis. Great. Thank you very much. Appreciate you. Write a function represented by the graph. Okay. This seems a little bit out of place, but we can do this one. All right. If we're going to write this function, guys, I just need to know 2 things. Thing number 1, right? What is my y-intercept? Thing number 2, what is the slope? That's all I need to write a function for this graph, okay? Identify the y-intercept. Here it is right here. This is the number 2. Identify the slope. Again, you can take some ordered pairs here. You can do whatever you want, guys. You can do the whole rise over run trick where you go up and then over. You just got to be careful about it. I know this line has positive slope because it's going uphill, all right? So we would find the slope of this line, guys, is also 2. So if we want to write a function, it did not say what form we had to use. Standard form, slope-intercept form. I choose slope-intercept form. The y-intercept is 2, the slope is 2. I'm replacing M and B, right? Here's my B, here is my M. So put it all together, guys. It looks like this, 2x plus 2. Okay? I think that's all we got to do there. Getting close, guys. Good news. I don't want to do the last 2 slides, right? If you're here in class for it, great. We'll go over it. We'll do it. But for the rest of you guys, right, we probably need to move on to some additional practice, right, with this, with these transformations. So our up, down, left, right moves, our compressions, our stretches, right, and then our reflections, okay? So that should be in our packet, I do believe. So go ahead, get going on that, and then we can check our work on it. Okay, hope you're doing well. Have a great day.